Okay, so in today's lecture, we are going to understand how the quantum state evolves over a period of time. Okay, so far, what we've studied is what are the allowable states of a quantum system. So if we have a k-level system, so classically it could take on one of k different states, then the state of the quantum system is a unit vector in a k-dimensional complex vector space. So this complex vector space is called a Hilbert space. So what we are told is that the state can be any point on the unit sphere in a k-dimensional complex vector space, and it can be written as a complex vector either in your standard notation or in the Ket notation like this. And the second thing we've studied so far is what happens when we measure the system. And what we've learned is that a measurement corresponds to the choice of an orthonormal basis for the space. The result of the measurement is one of k possibilities, each corresponding to one of the basis vectors. The probability of each basis vector outcome is the square of the inner product of the state vector with that basis vector. And moreover, if the outcome of the measurement is the ith basis vector, then the new state is exactly the ith basis vector. So for example, this is easiest to picture in 2 dimensions where your amplitudes happen to be real, so that you can plot everything out in a two-dimensional real space, and the state sits on the unit circle. And then the chance that if you measure in the 0, 1 basis or the standard basis, the chance that the outcome is 0 is cosine squared theta, and 1 is sine squared theta. The new state after the measurement is either the 0 state or the 1 state. Okay, so now what we want to understand is how does the state evolve in time? So let's look at the case of a qubit. So suppose that we have our qubit psi, which is this unit vector in a 2-dimensional vector space. What does the system do over time? What happens when forces act on the system, etc.? The answer is actually very elegant, very simple. So the evolution of the system corresponds to a rotation of the space. So think of it this way. We are sitting on the outside. We don't know what the state of this qubit is. And now we do something to the state to move it in time. And what we do is we take this Hilbert space, this 2-dimensional complex vector space, and we rotate it. So again, it's easier to picture in the real case. So what we do is take this circle and spin it through some angle. So every state gets rotated by some angle theta. Okay, that's the evolution of the state of a qubit. What this also means is that if instead of psi, the state of the system had been phi, then the new state would be some state phi prime, and the angle between psi and phi would be exactly equal to the angle between psi prime and phi prime. Okay, so let's try to see this in, more formally. So what does it mean that we are doing a rotation through angle theta? So what it means is that 0 gets transformed to cosine theta 0 plus sine theta 1, and 1 gets transformed to minus sine theta 0 plus cosine theta 1. Right? That's what a rotation through angle theta does to the basis vectors. But now rotation is a linear transformation, and so the way to write it is as a matrix, where what we are saying is that if you start with a state alpha 0 plus beta 1, then what it gets transformed to is, because rotation is a linear map, it should get transformed to alpha times cosine theta 0 plus sine theta 1 plus beta times minus sine theta 0 plus cosine theta 1. Right, and you can of course simplify this, and you get alpha cosine theta minus beta sine theta times 0 plus alpha sine theta plus beta cosine theta times 1. Okay, so the fact that rotation is a linear operation means that you can express it as a matrix. And of course, what should the matrix look like? Well, the columns of this matrix are exactly correspond to what the 0 state and the 1 state get transformed into. And so the columns of the matrix are cosine theta, sine theta, and then the second column is minus sine theta, cosine theta. And of course you can see this because where does 0 get mapped to? Well, you know, 0, the 0 state is in standard matrix notation, vector notation, it would be 1, 0. And so if you see where it gets mapped to, you'd get exactly this first column of the matrix. And similarly, 1 gets mapped to exactly the second column of the matrix. Okay, corresponding to this matrix, you can also write down the rotation through minus theta. The rotation through minus theta, you can check, would look like this. It's cosine theta, sine theta, minus sine theta, cosine theta. Okay, so it's just r of theta transpose. And of course, you know that if you do a rotation through theta and follow it by a rotation through minus theta, it's like you did nothing. So r of theta times r of minus theta is the identity, which in this case we can also say by saying r of theta times r of theta transpose equal to r of theta transpose times r of theta is the identity. Okay, so now actually we're in a place where we can state the basic axioms of quantum mechanics. So there are basically 3 axioms in quantum mechanics. The first one, the superposition principle, states what are the allowable states of a system. The second one, the measurement axiom, says what happens when you measure or look at the state of the system. And the third axiom, unitary evolution, tells you how the state of the system evolves in time. And this is a very beautiful, very elegant sort of formulation of quantum mechanics. The first axiom says the state of the system is a unit vector in a k-dimensional complex vector space. So if it's a k-level system, we have a k-dimensional complex vector space. And the state of the system can lie anywhere on the unit sphere. The second axiom, the measurement axiom, says if you want to measure, you have to reach into this Hilbert space. And the way you reach in is you pick an orthonormal basis, you measure, and the state collapses into one of the basis vectors of this orthonormal basis. Which one? Well, it collapses onto a random one, the jth one with probability cosine squared theta, where theta is the angle between the state vector and the jth basis vector. So it's the square of the magnitude of the inner product between the state vector and the jth basis vector. Moreover, the result of measurement is that the state collapses to the jth basis vector. The last axiom of unitary evolution says the quantum state evolves by rigid body rotation of the Hilbert space. So what you do is, you know the state of the system is some unit vector at some point on the unit sphere in this k-dimensional complex Hilbert space. What you can do is you can take the sphere and rotate it. That's what a transformation of the evolution of the system looks like. It's some rotation along some axis. And then what this rotation does is the state now evolves because of this rotation. Everything gets carried in some direction, and you get the new state of the system. Okay. So it's that simple. Those are the three basic axioms of quantum mechanics that tell you what the states of the system are, how they evolve in time, what a measurement is. Okay. Now, of course, it's a much longer story than this. To really understand what all this means will take us a lot of time. In particular, for the rest of the lecture, we'll try to understand formally what it means to do a rigid body rotation of the Hilbert space.